So, good afternoon. Today we have as an invited speaker, Professor Lorenz Willman. Professor Lorenz Willman is now a professor in the Van Winter Institute of Particle Physics in the University of Groningen, where I did my PhD with. We will talk today about experimental techniques to study the Standard Model. So, thank you for coming, and it's all yours.
Well, thank you very much. It is definitely a pleasure to be here, being invited by Maya and Alejandra, and also to work in the lab with quantum optics, which is more the photon side of that segment of the interaction. So it's also a standard model, it's very deep in there. And yes, that has been very, very nice, and I'm definitely looking forward to coming back in October to extend this further. So the title of my talk has the two aspects of that one. What I'm interested in my experimental physics is the Standard Model, so I will briefly say some things which connect to the physics which we are doing with that, but also ask the question, what is it actually what we're observing, and how do we actually know something then about the Standard Model? How do we learn something about it, and go a little more in the details on these aspects. There's a time, that's a good thing to look at. Please ask at any moment when you have questions, because it's more the idea of a discussion here. I have probably far too many things. And then we can discuss things more in detail. So here I'm saying it's particles with interactions. That is the Standard Model. It's both of that one. That's what we are understanding. And now I go far back historically, and I introduce the hydrogen atom because that comes back in a moment. I work with that. And there are, we all have learned this, there are these different layers of concepts. Bohr came up first with this discrete spectrum of that one as a proposal, and that is by introducing an additional constraint, which is essentially that the electron wave function, the Bohr had introduced that the electron is also a wave function, actually matches the circumference, and if you solve that, you get to quantized levels, and that's a Bohr model. And it comes out with very simple formulas. And if you look now for the development on that one, this is the 1/n² energy level of the lowest line level, the next one, and so on. And then physics developed further. In a closer look at these things, people realized that actually the n=1 level is actually shifted a little bit down. The n=2 level has 3 sublevels, but still only 2 are still degenerate, and that was due to Dirac, who introduced essentially relativity and resulted in the fine structure of that system. And interestingly enough, these 2 levels were still degenerate, and physics actually doesn't really like degenerate levels. And there was the relativity. In the next level, we have quantum electrodynamics. That's a lamp shift, and that splits again these S and P levels a little bit. And as a further complication or addition, where we can learn something about physics and the atomic system, where information is hidden in that one, is because the proton has also some structure. In particular, it has a nuclear spin, and then we get a fine structure. It's actually not everything. The proton also has an extent, and that also comes back in the spectrum, which you see there. But we don't want to go much further than that. So it's just the development that we see how we can get to these different layers and get a more complete picture. And we want to now look a little bit about signals, what tells us that. And also, it's not very clear. This is not the end. It could be that there is some other additional structure coming, which we have not yet observed. And that could be, for example, due to atomic parity violation, in the weak interaction there should be a little splitting in there, but it's not observable with the current means what we have right now. Or things like permanent electric dipole moments. So another simple cartoon of that one is that we, down here are some years which are relevant for that. A little cartoon of that one is our four forces which we have here. The gravity, the electromagnetic forces is the most well-known forces which we have here. The strong force, which is for the nucleus, and the weak force, which is for all particles. And one thing I've listed here is that there is a different strength associated with that. The electromagnetic force and gravity have something in common. It's their distance behavior. That the force falls off as 1/r², but the electromagnetic force is 38 orders of magnitude larger than the gravitational force. That's why we have this big mismatch. It's very difficult to combine these two. But mathematically, it's rather similar, except that we have the plus and the minus, and we don't have the mass and the anti-mass in there. In here is depicted that an atom actually shares all these different forces in there. It's mainly the electromagnetic force. It is gravity, which we can play with. There's a weak force in atoms, which is very interesting. That's what I'm interested in, but it's in there. And the strong force also contributes to the atomic spectra. And the strong force is called strong because it's indeed even stronger. At a given length scale, it falls off much faster. Thank you. Falls off much faster with a distance as the electromagnetic and the gravity. As a consequence, just to say that the bosons, the gauge bosons, which are responsible for these forces, what we can learn from this one, that if it's a 1/r² behavior, then the gauge bosons are massless. And in the case for the weak interaction, it's not massless, also for the strong interaction. So it looks like, first of all, a bunch of forces which we have there, but in the past there have been the unification of these forces, and I think it really started with Maxwell, who put electricity, magnetism, and essentially light together. And then we have beta decays and neutrinos, and that came to a decent theory in 1965 to explain the weak interaction. Then we have the strong interaction, that's essentially QCD, which explains that. And we have, on the bottom, we have our gravity, which is the odd one out, which we cannot explain so well at the moment. And in the meantime, things have happened. The beginning of the standard model is actually really the unification of the electromagnetic and the weak interaction, realizing, although they have a different length scale behavior, as I had shown in the previous slide, they are actually can be described in a common framework. It's the same interaction, and that is what we will come back to. And combining these three, that is essentially our standard model. The standard model itself is also not a static model. It's not the same which was written down in 1976. It is something which develops. There are things added to the standard model. For example, the neutrinos were treated as massless particles in a theory of the weak interaction. By now we actually know that neutrinos have a finite mass. It's incredibly small and hard to measure. But that's essentially incorporated in the standard model. And there's this, then there's a general relativity, which comes down here. And people hope that there is some unification of that one, but that is a very difficult question. And yes, I'm working in an institute which is called for particle physics and gravity. So I have my colleagues in this. And this is a nice poster. I think it was issued for one of the Nobel Prizes on the standard model. It actually summarizes everything in the standard model, and that is how we can, in physics, put a lot of things together. All these aspects are in here. This is a neutron decay, so that's weak interaction, that's scattering of hadronic, leptonic to hadronic interactions. Here we have essentially the same picture, that we have an atom, the nucleus has quarks, and this is a strong interaction here, but there's a shell of electrons, so it is always, it comes to the same information. Yeah, it's surprisingly simple in some way, that we can do so much with it. But some of the really nice features of this model is that that there are symmetries built in that. And the one symmetry is a parity, is a left-right symmetry or the mirror symmetry, or actually parity is the inversion at the origin of the spatial coordinates. And if you do a parity transformation, you cannot get this parity transformed object by any rotation or translation to overlap with the other one. That's the left and the right hand, they don't match up. And maybe because I have trouble to distinguish between left and right, I think it's an interesting question. This is something, and actually parity as a concept came out of atomic physics in the 1920s, because that's the selection rules in atoms which tell you what transitions are allowed. It's that the parity of the photon is -1. So the states which I have between two levels in an atom have to have opposite parity. And that was very well tested, that this parity is a good quantum number. A little more complicated is the charge, or the other symmetry is the charge conjugation, that for each particle which we have also an antiparticle. And they share the same properties except the charge. They have opposite charge in that. And if they don't, then it is a problem. And the other thing which we also rely on, that every process which runs in the forward direction can also run in the backward direction. That's time reversal symmetry. And to some extent it is also connected to fundamental constants. We have fundamental constants in our theory, that is, for example, the fine structure constant alpha, which is essentially the electron charge, or the weak interaction, or many other constants, the speed of light, h bar. We treat them as constants, but it's still, it could be questioned, are they actually constant? And that all fits together is a good starting point for experimental research to check if this is true. So if we then summarize a little bit the standard model in this, the standard model is an excellent description of all observations. That's what it's actually aiming for. And also, within this framework of this excellent description of the observations, to make predictions. And there have been some predictions made in the standard model which are good. But there are also observations in the standard in nature, for example, parity violation, that this simple symmetry, which is obeyed by the electromagnetic interaction, is violated in the weak interaction. So actually, every weak process is parity violating. It's maximally parity violating. There is another level, which is the so-called CP violation, the combined symmetry of particle, antiparticle, and parity, which is actually in the weak interaction of the nuclear beta decay or the muon decay. CP is a good quantity, it's conserved, but in other systems CP is violated. It's not necessarily a good symmetry. Also we have the, what astronomers like to say, there's an asymmetry in the observed matter in the university and antimatter, there's the antimatter missing. That is also closely related to questions on CP violation, because CP violation, beyond what we know in the standard model, can actually give an explanation for that problem, how this actually came along. So, it's great, but there are open questions in there. There are many models which I am not so knowledgeable about, but the supersymmetry is very simple. You add to every particle, you have another supersymmetric particle. You actually double the number of particles which are available in the universe or in your Lego system, and that definitely offers more symmetries and more things which can be used to explain. These new models sometimes motivate parity violation or actually invent sources of CP violation. So that is the theoretical part which contributes a lot to that. Maybe the other thing on the standard model is it consists out of 3 family of particles. We have 3 forces. As we said, we have the strong force, the weak force, and the electromagnetic force. Gravity is not yet included in that. And there are 30 parameters. These are essentially these fundamental constants I was referring to. And that's all. And not more. That's the full description. So now, with what I do, I cannot explain the whole thing, but I can ask the question, how can I actually get to learn something about the standard model, which experiment could be done, and what do I have to do in my experiment to do that? Now we come more to the experimental part of what I wanted to talk. And that is what atomic physics has taught us. We can achieve actually a very, very high precision in measurements with coherent excitations of light and matter, and extract a lot of information from this. So we actually get many, many digits of precision on a particular quantity, and that allows us to see if the measurement deviates a little bit from our expectations. We can say, well, that might be due to something which we had not included in the standard model yet. And precision aims at the questions about matter, antimatter, or dark matter. I have not mentioned this. And it can be addressed in particle physics at really high energies at a collider. This is a picture of the CERN area, and this is this 27 kilometer long LHC ring. This is SPS, which is underground. And also it can be addressed in atomic physics type of experiment. And this doesn't, I don't want to imply that this has nothing to do with precision, because high energy experiments are also aiming at precision means actually something, and that means how good can I do a measurement? Can I actually have a model describing that thing which I'm investigating? Is it worthwhile to look for that? I can also count with a high precision the number of leaves on a tree, but it doesn't give me more insights in some aspects of nature. So can I give a background theoretical what I want to do there, and then together with this one I can probe sensitivity to physics, or probing it, looking for new additions to the physics. So my generic experiment, because I'm more doing this with atomic systems, is we do something with lasers on a laser table, and I think this is Albert. You cannot recognize him, so this is a former colleague of Mayerlin. Then there is the stuff you want to investigate, the interaction of your system, and in the end you get somehow a signal of some interesting shape, and the signal tells you something about the interaction, because first of all this is a model, but here is our information which tells us what actually has happened. And also the readout signal, that was a long arrow, tells us then something about the parameters, because my experiment depends certainly always on a lot of different parameters. So I want to discuss a little bit what you actually do with this. How do you get to good understanding of what it actually is, and it's a what does it mean? I want to say a reliable extraction of these particles. So it actually also has something to do with understanding error bars on these points. And that brought me